The Big Bang theory is widely accepted by most scientists as the primary explanation for the origins of the universe, encompassing the creation of stars, planets, and all life therein, including us. Despite its somewhat whimsical name, the term Big Bang aptly captures the enormity of the event. Initially, the universe was a dense collection of particles packed into a space smaller than a pinhead. From this minuscule point, a massive explosion of matter occurred, known as the Big Bang. This succinctly summarizes the process that unfolded over billions of years. However, despite the enduring popularity of the Big Bang theory, advancements in scientific data have increasingly challenged its predictions. When NASA launched the James Webb Space Telescope, the largest and most advanced space observatory to date, scientists anticipated that its observations would bolster the Big Bang theory. Sadly, after just 1 year in space, the telescope has astonished scientists with its remarkable capabilities, providing unprecedented glimpses into the universe's past. The James Webb Telescope's discoveries have unveiled galaxies so ancient that they could potentially reshape our understanding of the universe's origins. This unforeseen revelation has sparked intense curiosity among scientists and enthusiasts alike. One such groundbreaking discovery came when astronomer Rohan Natu, analyzing early images from the James Webb Telescope, stumbled upon a galaxy that defied expectations. This galaxy, named Glass Z13, appeared inexplicably massive and dated back to a mere 300 million years after the Big Bang, making it older than any previously observed galaxy. Nata's excitement was palpable as he shared the discovery with colleagues in the world, describing it as beyond astronomers' wildest dreams. The James Webb Telescope, stationed far from earthly interference and equipped with cutting-edge technology, was designed to delve into the universe's earliest epoch, known as Cosmic Dawn. This era, shrouded in mystery, marks the formation of the universe's first stars and galaxies. By scrutinizing galaxies from this period, scientists hope to refine their understanding of fundamental cosmic processes, such as the influence of dark matter and dark energy. Initial expectations for the James Webb Telescope's findings were modest, anticipating only a few faint distant galaxies. However, the reality exceeded all projections. The telescope's images revealed galaxies of surprising maturity, challenging existing models and prompting a flurry of research activity. As scientists continue to analyze the James Webb Telescope's data, the implications of these discoveries could be profound, ushering in a new era of cosmological understanding. The unexpected revelations from this groundbreaking observatory offer a tantalizing glimpse into the universe's past, driving humanity's quest to unravel the mysteries of existence. As early galaxies came into view, theorists and observers found themselves in a scramble to explain them. Could this bevy of anomalously big and bright early galaxies be an illusion, perhaps due to flaws in the analysis of the telescope's initial observations? Or, if genuine, could they somehow be reconciled with standard cosmological models? Or just maybe, were they the first hints that the universe is more strange and complex than our boldest theories had supposed? At stake is nothing less than our understanding of how the orderly universe we know emerged from primordial chaos. The early revelations from the James Webb Space Telescope have the potential to rewrite the opening chapters of cosmic history. These chapters not only concern distant epochs and faraway galaxies, but also our own existence here in the familiar Milky Way. As Mark McCarran, a senior advisor for science and exploration at the European Space Agency involved in JWST, remarked, "You build these machines not to confirm the paradigm but to break it. You just don't know how it will break." One might say that JWST's observations of early galaxies have been billions of years in the making. However, more modestly, they trace back to the Space Telescope Science Institute in 1985. At that time, the Hubble Space Telescope was still 5 years away from launch, but the Institute's then-director Riccardo Giacone asked his team to start thinking about what would come after Hubble much farther down the road. Despite initial protests about focusing on Hubble, Giacone was insistent, foreseeing the lengthy development process. Gillinger, then deputy director of SD-Sky, along with a small team, began drafting ideas for what eventually became the next-generation space telescope, later renamed JWST. They recognized that while Hubble would be transformational, its capabilities would be limited by its observations in visible light. The NGST, on the other hand, would observe in the infrared spectrum, allowing it to penetrate deeper into the universe. The need for JWST became even more apparent in December 1995 when astronomers conducted the Hubble Deep Field observation. Despite expectations of finding only a few dim galaxies, the resulting image revealed thousands of galaxies stretching back over 12 billion years into the universe's history. After more than 2 decades of development and at a cost of around $10 billion, JWST finally launched on Christmas Day 2021. The telescope underwent exhaustive testing before reaching its deep space destination a month later. By July 2022, it was ready to commence its long-awaited first year of science observations, known as Cycle 1. Part of JWST's early mission was devoted to high-impact programs, including the Cosmic Evolution Early Release Science Survey and the GRISM Lens Amplified Survey from Space, both aimed at shedding light on the mysteries of the early universe. As astronomers independently devoted countless hours to scanning separate patches of the sky in search of early universe galaxies, they initially anticipated modest findings akin to a more intricate version of the Hubble Deep Field. However, they were in for a surprise. Stephen Finkelstein from the University of Texas at Austin, leading the SEERS project, explains that extremely distant galaxies were expected to emerge only after multiple data cycles from various programs. Yet, to astronomers' astonishment, these galaxies appeared almost immediately. Previously, the record for the most distant known galaxy belonged to GNZ 11, spotted in 2015, with a redshift of 11. Redshift measures the stretching of light due to the universe's expansion, with a higher value indicating greater distance. But from the outset of GLASS observations, 2 separate teams, including one led by Rohan Natu, independently identified GLASS Z13 with a redshift of 13, pushing the cosmic timeline back even further. In their haste for rapid results, researchers relied on simplified techniques for redshift estimation based on brightness measurements rather than more time-intensive direct measurements. Despite their simplicity, these estimates revealed galaxies unexpectedly bright and massive, some already boasting a stellar mass rivaling 1 billion suns, akin to our own Milky Way, which is billions of years more mature. The excitement didn't stop there. In the ensuing days, numerous galaxy candidates from SEERS and GLASS emerged, some with redshift estimates as high as 20, indicating they existed a mere 180 million years after the Big Bang. These galaxies displayed disk-like structures not anticipated in such early cosmic epochs. Additionally, another team discovered evidence of Milky Way-sized galaxies at a redshift of 10, less than 500 million years after the Big Bang. Such rapid emergence of sizable galaxies challenges the predictions of the standard cosmological model, lambda cold dark matter. To comprehend this anomaly, a brief revisit to early universe dynamics is necessary. In the initial moments after the Big Bang, the universe was a hot, dense soup of primordial particles. Over time, as the cosmos expanded and cooled, helium and other light elements formed, leading to the appearance of the first atoms around 400,000 years later. Roughly 100 million years after the Big Bang, conditions became conducive for the formation of the first stars, composed primarily of hydrogen and helium. The early stars, larger and brighter than modern stars, aggregated into protogalaxies, guided by the gravitational pull of dark matter. However, JWST's discovery challenges this model, as it reveals bright, sizable galaxies far earlier than predicted. Stacy McCore from Case Western Reserve University notes the unexpected absence of numerous smaller protogalactic fragments, suggesting that some observed galaxies may be closer than presumed, veiled by dust and appearing dimmer and more distant. The revelation of these early galaxies raises profound questions about the universe's formative years, underscoring the necessity for continued exploration and revision of our cosmological models. Follow-up observations of GLASS Z13 in August 2022 by the Atacama Large Millimeter Array in Chile cast doubt on the initial findings. Despite the use of brightness-based measurements, ALMA did not detect significant amounts of dust gas.